Hello everyone, this is Bhumika Mohan. In this video, I am going to discuss a topic that is related to analysis and design of algorithms, that is merge sort with time efficiency. So coming to the contents of this video, first I'm going to give an introduction to merge sort, then divide and conquer strategy, logic of merge sort, algorithm of merge sort, and an example. Then I'm going to talk about analysis of time complexity, some advantages and disadvantages of merge sort, applications of merge sort, and lastly conclusion. So, coming to the introduction to Mozart, Mozart is one of the most popular sorting algorithms that is based on the principle of divide and conquer algorithm. Here, a problem is divided into multiple subproblems. Each subproblem is solved individually. Finally, subproblems are combined to form the final solution. It can also be defined as the divide and conquer algorithm that sorts an array by first breaking it down into smaller arrays and then building the array back together the correct way so that it is sorted. Divide and conquer strategy. A divide and conquer algorithm is a strategy of solving a large problem by first breaking the problem into smaller subproblems. Second is solving the subproblems and then combining them to get the desired output. To use the divide and conquer algorithm, recursion is used. Using the divide and conquer technique, we divide a problem into subproblems. When the solution to each subproblem is ready, we combine the results from the subproblems to solve the main problem. Suppose we had to sort an array A subproblem would be to sort a subsection of this array starting at index P and ending at index R, denoted as A, P to R. The first step is divide. If Q is the halfway point between P and R, then we can split the subarray A P to R into two arrays, that is A P to Q and A Q plus 1 to R. Second is conquer. In the conquer step, we try to sort both the subarrays, that is A P to Q and A Q plus 1 to R. If we haven't yet reached the base case, we again divide both these subarrays and try to sort them. The third step is combine. When the conquer step reaches the base step and we get two sorted subarrays, that is A P to Q and A Q plus 1 to R for array A P to R, then we combine the results by creating a sorted array, that is A P to R, from two sorted subarrays, that is A P to Q and A Q plus 1 to R. So coming to the logic of merge sort, first divide the unsorted array into two subarrays, half the size of the original. Second is to continue to divide the subarrays as long as the current piece of the array has more than one element. The third is merge two subarrays together by always putting this lowest value first. And lastly, keep merging until there are no subarrays left. So the algorithm of merge sort is, first, we write that the algorithm merge sort 0, low, and high. So this sorts the given array by recursive merge sort. Import of this merge sort is an array A0 to n minus 1 of orderable elements, and the output is array A0 to n minus 1 sorted in non-decreasing order, that is the increasing order. So the algorithm of merge sort is, if low is less than high, then we take that mid equals low plus high by 2. And here is the recursive function, that is merge sort A low mid and merge sort A mid plus 1 high. Then we write that the merge A low mid and high, which is used to combine the sorted arrays. So here is an example for merge sort. Step 1, we start with an unsorted array and we know that it splits in half until the subarrays only consist of one element. The merge sort function calls itself two times, once for each half of the array. That means that the first subarray will split into the smallest pieces first. So the unsorted array here is 12, 8, 9, 3, 11, 5 and 4. Here we take that the mid as 3 and the first subarray is 12, 8, 9 and the second subarray is 3, 11, 5 and 4. The 12, 8, 9, that is the first subarray, is further divided into 12 and another array 8 and 9, and the second array is 3, 11, 5 and 4. The array subarray which consists 8 and 9 is divided further, so this array becomes 12, 8, 9, and a second array that is 3, 11, 5, and 4. Step 2 is splitting of the first subarray is finished, and now it is time to merge. 8 and 9 are the first two elements to be merged. 8 is the lowest value, so that comes before 9 in the first merged subarray. So here it is shown that 12 is a separate array, 8 and 9 have been combined, and another array is 3, 11, 5, and 4. Coming to step 3, the next subarrays to be merged is 12 and 8, 9. Values in both arrays are compared from the start. 8 is lower than 12, so 8 comes first, and 9 is also lower than 12. So here we can see that the first array consists of 8, 9, 12, and the second array consists 3, 11, 5, and 4. So step 4 is now the second big subarray is split recursively. That is 3, 11, 5, 4. We keep the sorted array 8, 9, 12 as it is, and the 3, 11, 5, 4, that is the second array is split as 3, 11, and 5, 4. We also see that the 3 and 11 array is further divided to 3 and 11. Step 5. 3 and 11 are merged back together in the same order as they are shown because 3 is lower than 11. That is 8, 9, 12. That is the sorted array remains as it is, and 3 and 11 are merged, and 5 and 4 array is kept as it is. Coming to steps 6, subarray with values 5 and 4 is split, then merged so that the 4 comes before 5. 8, 9, 12 is a sorted array, 3, 11 is another sorted array, and 5 and 4 are split here. Then we merge it back together so that it becomes 8, 9, 12 as an sorted array, and 3, 11 is another sorted array, and 4 and 5 is another sorted array. Step 7 is the two subarrays on the right are merged. Comparisons are done to create elements in the new merged array. That is, 3 is 11 is lower than 4, 4 is lower than 11, 5 is lower than 11, 11 is the last remaining value. So this becomes 8, 9, 12 as one sorted array, and 3, 4, 5, 11 as another sorted array. So coming to step 9, 4 is lower than 8, so no, the two subarrays on the right are merged. Comparisons are done to create elements in the new merged array. So here is the array that is 8, 9, 12 and 3, 4, 5, 11. Step 8 is the two last remaining subarrays are merged. Let's look at how the comparisons are done in more detail to create the new merged and finished sorted array. 3 is lower than 8. So before this merging takes place, sorting and merging takes place, the two sorted arrays are 8, 9, 12 and 3, 4, 5, 11. And after the sorting and merging, it looks as 3, 8, 9, 12 and 4, 5, 11. Step 9 is 4 is lower than 8. So before the sorting and merging, it is 3, 8, 9, 12 and 4, 5, 11. And after it looks like 3, 4, 8, 9, 12 and 5, 11. Coming to step 10, 5 is lower than 8. So it becomes 3, 4, 5, 8, 9, 12 and 11. And coming to step 11, 8 and 9 are lower than 11. So the sorted array looks as 3, 4, 5, 8, 9, 12 and 11. And coming to step 12, 11 is lower than 12. So after the process is done, the sorted array looks as 3, 4, 5, 8, 9, 11, 12. The sorting is finished according to merge sort. So this is the diagram of the process of the merge sort. Coming to analysis of time complexity, merge sort is a recursive algorithm, and time complexity can be expressed as following recursive recurrence relation, that is T of n equals to Tn by 2 plus O of n. The solution of the upper recurrence is O n into log n. The list of size n is divided into a max of log n parts, and the merging of all sublists into a single list takes O n time. The worst case runtime of this algorithm is O n into log n. Best case time complexity is O n into log n. Worst case time complexity is also O n into log n. Also, average time complexity is O n into log n. So the time complexity of merge sort is O n into log n in all the three cases, that is worst, average, and best, as the merge sort always divides the array into two halves and takes linear time to merge two halves. Coming to advantages and disadvantages of merge sort. Advantages are consistently good performance O n into log n regardless of input. Also, as a stable sorting algorithm. Coming to the disadvantages, it requires additional space proportional to the size of the input list. Generally, slower than in-place sorting algorithms like quicksort and heap sort in practical use due to the overhead of merging and additional space. Some of the applications of merge sort are database management. When sorting records based on multiple keys, merge sort ensures that records with the same key retain their relative order from the original dataset. Second one is event scheduling. In applications where events have the same priority or timestamp, stable sorting maintains the original sequence of events. Third one is linked lists, where the merge sort is very efficient for sorting linked lists. Since it doesn't require random access to data, it can sort linked lists in any login time without needing additional space proportional to the size of the input. The fourth one is inversion count, where the merge sort can be modified to count the number of inversions in an array. That is, where an inversion is a pair of in elements that are out of order. So another application of Mozart is big data processing, where in systems like Hadoop, Mozart is part of the sorting mechanism for processing large-scale data distributed across many machines. Disk-based sorting. For applications that involve large amounts of data on disk, Mozart is used to handle sorting efficiently by minimizing disk I/O operations. Coming to parallel algorithms, in parallel computing environments, Mozart can be divided into subproblems that can be solved concurrently, making it suitable for multi-core processes and distributed systems. Another application of Mozart is merging logs, in scenarios where multiple log files need to be merged into a single chronological log, Mozart ensures efficient and orderly merging. Coming to TimSort, a hybrid sorting algorithm used in Python and Java combines merge sort and insertion sort to handle real-world data efficiently. And it is also used in e-commerce applications. So here's a conclusion. Merge-sort is a versatile and efficient sorting algorithm with several practical applications, particularly in scenarios where stability and predictable performance are crucial. Merge-sort's predictable performance and stability make it a powerful tool for many practical applications. Thank you.